Derivation of the variation of parameters formula for a second-order linear, ODE. Imagine you have a nice homogeneous spring mass system described by a second-order linear ODE with variable coefficients, y double prime plus p of x y prime plus q of xy equals 0. The two independent solutions y sub 1 of x and y sub 2 of x are like two different ways the spring can move without any external push. They form a basis for all possible free motions. When an external force g of x acts, the equation becomes y double prime plus p of xy prime plus q of xy equals g of x. The idea of variation of parameters is to let the constants that multiply y sub 1 and y sub 2 become functions of x. Y sub p of x equals u sub 1 of x times y sub 1 of x plus u sub 2 of x times y sub 2 of x. Why does this make sense? Think of a marching band. Each musician follows a basic rhythm, the basis solutions, but the conductor can ask each to speed up or slow down, the variable parameters, to match a new song, the forcing term. To find u sub 1 and u sub 2, we impose an extra condition that simplifies the algebra. U prime 1 of x times y sub 1 of x plus u prime 2 of x times y sub 2 of x equals 0. This condition removes the second derivatives of u1 and u2 when we substitute y sub p into the original ODE after substitution, and using the fact that y sub 1 and y sub 2 satisfy the homogeneous equation, we are left with a single linear system for u prime 1 and u prime 2. U prime 1 of x times y prime 1 of x plus u prime 2 of x times y prime 2 of x equals g of x. And u prime 1 of x times y sub 1 of x plus u prime 2 of x times y sub 2 of x equals 0. Solving this system, usually with Kramer's rule, gives the famous variation of parameters formulas. The particular solution y sub p is obtained by integrating u prime 1 and u prime 2. Finally, the general solution is y of x equals c1 times y sub 1 of x plus c2 times y sub 2 of x plus y sub p of x. The Wronskian is a determinant that measures how independent two functions are, much like checking whether two vectors point in different directions. For two candidate solutions y sub 1 and y sub 2, we define w of y sub 1, y sub 2 of x equals the determinant of a 2 by 2 matrix with entries y sub 1 of x, y sub 2 of x, y sub 1 prime of x, y sub 2 prime of x. This equals y sub 1 of x times y sub 2 prime of x minus y sub 2 of x times y sub 1 prime of x. If w is not equal to 0 at some point, the two functions are linearly independent on an interval containing that point, guaranteeing they span the solution space of the homogeneous equation. In the variation of parameters derivation, the Wronskian appears naturally when we solve the 2 by 2 linear system for u sub 1 prime and u sub 2 prime. Using Kramer's rule, we obtain u sub 1 prime of x equals negative y sub 2 of x times g of x divided by w of y sub 1, y sub 2 of x. U sub 2 prime of x equals y sub 1 of x times g of x divided by w of y sub 1, y sub 2 of x. Thus the Wronskian sits in the denominator. If it were 0, the formulas would blow up, signaling that our chosen y sub 1 and y sub 2 are not a proper basis. In practice, one can compute w directly or use Abel's identity, which says for y double prime plus p of xy prime plus q of xy equals 0 that w of x equals w of x sub 0 times exponential of negative the integral from x sub 0 to x of p of t dt. This tells us that once w is non-zero at a single point, it never becomes 0 on the whole interval. A comforting real-world analogy is a river that never dries up once it has a source flow. Write the ode in standard form. Y double prime plus p of x times y prime plus q of x times y equals g of x. Ensure the coefficient of y double prime is 1. Divide if necessary. Find two linearly independent solutions of the homogeneous part g equals 0. Call them y1 of x and y2 of x techniques, guess and check, reduction of order or power series. Compute the Wronskian w of x equals y1 times y2 prime minus y2 times y1 prime. Verify w not equal to 0 on the interval of interest. Set up the system for the parameter derivatives using the auxiliary condition u1 prime y1 plus u2 prime y2 equals 0. The system is u1 prime y1 prime plus u2 prime y2 prime equals g of x, and u1 prime y1 plus u2 prime y2 equals 0. Solve for u1 prime and u2 prime using Kramer's rule. u1 prime equals negative y2 of x times g of x divided by w of x. u2 prime equals y1 of x times g of x divided by w of x. Integrate to obtain u1 of x equals the integral of u1 prime of x dx, and u2 of x equals the integral of u2 prime of x dx. Choose any convenient antiderivative. Constants of integration can be set to 0 because they would merely duplicate the homogeneous part. Form the particular solution y sub p of x equals u1 of x times y1 of x plus u2 of x times y2 of x. Write the general solution. Y of x equals c1 y1 of x plus c2 y2 of x plus y sub p of x. Check by plugging y of x back into the original ode. Any algebraic slip will be caught here. This algorithm works even when p of x and q of x are messy, which is why engineers love it for variable coefficient models such as a beam with non-uniform stiffness. Standard form, the equation already has the leading coefficient 1. So p of x equals 0, q of x equals 1, g of x equals sec x. Homogeneous solutions. Solve y prime plus y equals 0. Characteristic equation r squared plus 1 equals 0 gives r equals plus minus I, hence y sub 1 equals cos x and y sub 2 equals sin x. Wronskian, W equals determinant of matrix with entries cos x, sin x, negative sin x, cos x, which simplifies to cos squared x plus sin squared x equals 1. Parameter derivatives. U sub 1 prime equals negative y sub 2 times g divided by w, which is negative sin x times sec x equals negative tan x. U sub 2 prime equals y sub 1 times g divided by w, which is cos x times sec x equals 1. Integrate u sub 1 of x equals integral of negative tan x dx, which is natural log of absolute value of cos x plus c sub 1. U sub 2 of x equals integral of 1 dx, which is x plus c sub 2. We set c sub 1 and c sub 2 equal to 0 because any constant would merge with the homogeneous part. Particular solution. Y sub p equals u sub 1 times y sub 1 plus u sub 2 times y sub 2, which equals natural log of absolute value of cos x plus x times sin x. General solution. Y of x equals c sub 1 cos x plus c sub 2 sin x plus cos x times natural log of absolute value of cos x plus x sin x. Interpretation. The term cos x natural log of absolute value of cos x reflects how the external force sec x, which blows up at odd multiples of pi over 2, modifies the natural oscillation, while the x sin x term adds a slowly growing amplitude, analogous to a pendulum being pushed periodically with a force that gets stronger near certain angles. A second-order ordinary differential equation can always be written as a two-dimensional first-order system. More generally, consider y prime equals a of x times y plus g of x. Where y belongs to blackboard bold r superscript n, a of x is an n by n matrix of functions, and g of x is the forcing vector. The homogeneous system, g equals 0, has a fundamental matrix phi of x, whose columns are n independent solution vectors. Variation of parameters says look for a particular solution of the form y sub p of x equals phi of x times u of x, where u of x is now a vector of unknown functions. Differentiating gives y sub p prime equals phi prime times u plus phi times u prime. Because phi prime equals a times phi, the columns satisfy the homogeneous equation. The term phi prime u equals a phi u equals a y sub p. Substituting into the original system cancels the a y sub p terms and leaves phi of x times u prime of x equals g of x. Multiplying by phi inverse of x gives the simple formula. U prime of x equals phi inverse of x times g of x. U of x equals the integral of phi inverse of x times g of x with respect to x. Finally, y sub p of x equals phi of x times the integral of phi inverse of x times g of x with respect to x. The analogy is the same as before. The homogeneous solution matrix phi supplies the basis directions, and the integral adjusts the weights, the parameters, to accommodate the external input g. This matrix version works for any size n, and is the backbone of control system analysis, where g is an input signal. Standard form, y double prime minus 3y prime plus 2y equals e to the 2x. Here p of x equals minus 3. Q of x equals 2, g of x equals e to the 2x. Homogeneous equation, y double prime minus 3y prime plus 2y equals 0. Characteristic equation r squared minus 3r plus 2 equals 0, which factors to r minus 1 times r minus 2 equals 0. Thus y sub 1 equals e to the x, y sub 2 equals e to the 2x. Wronskian, W equals the determinant of the matrix with entries e to the x, e to the 2x in the first row, and e to the x, 2e to the 2x in the second row. This equals e to the x times 2e to the 2x minus e to the 2x times e to the x, which simplifies to e to the 3x. It is never 0. Parameter derivatives. u1 prime equals negative y sub 2 times g divided by w, which is negative e to the 2x times e to the 2x over e to the 3x, equals negative e to the x, and u2 prime equals y sub 1 times g divided by w, which is e to the x times e to the 2x over e to the 3x, equals 1. Integrate, u1 of x equals the integral of negative e to the x dx, which is negative e to the x plus c1. u2 of x equals the integral of 1 dx, which is x plus c2. Set c1 and c2 equal to 0 for the particular part. Particular solution. Y sub p equals u1 times y sub 1 plus u2 times y sub 2, which is negative e to the x times e to the x plus x e to the 2x, simplifying to negative e to the 2x plus x e to the 2x, which equals x minus 1 e to the 2x. General solution. Y of x equals c1 e to the x plus c2 e to the 2x plus x minus 1 e to the 2x. Simplify if desired. Y of x equals c1 e to the x plus c2 plus x minus 1 e to the 2x. Exam tip. Notice that the forcing term e to the 2x is already a solution of the homogeneous equation, which is why the particular solution acquires an extra factor of x. The method of annihilators would give the same result. Variation of parameters automatically produces this factor through the integral of u2 prime. Explanation: common pitfalls and checks, for example linear independence, division by 0 in exam solutions. Forgot to verify linear independence. If y sub 1 and y sub 2 are not independent, the Wronskian is 0, leading to division by 0 in the formulas for u1 prime and u2 prime. Always compute W or use Abel's theorem before proceeding. Using the wrong auxiliary condition. The condition u1 prime y sub 1 plus u2 prime y sub 2 equals 0 is essential. Dropping it adds unnecessary u1 double prime and u2 double prime terms and makes the algebra messy. Skipping the integration constants. When integrating u1 prime and u2 prime, many students set the constants to 0 automatically. This is fine for the particular solution because any constant would just merge with c1 y sub 1 plus c2 y sub 2. However, write a short note explaining why you discard them. Exam markers like to see the justification. Sign errors. The formulas have a minus sign on u1 prime but not on u2 prime. A quick sanity check is to plug a simple forcing, for example g of x equals 0. Both u1 prime and u2 prime should become 0. Domain issues. Functions like secant x or ln absolute cos x have restricted domains. Mention the interval where the solution is valid, for example x in open parenthesis minus pi over 2 comma pi over 2 close parenthesis for the secant example. Algebraic simplification. After finding y sub p, always substitute back into the original ordinary differential equation, or at least check a derivative to catch algebra slips. A quick numeric check at a convenient point, say x equals 0, can reveal sign mistakes before time runs out. Misidentifying the homogeneous solutions. For variable coefficient ordinary differential equations, students sometimes guess constant coefficient forms and get wrong y sub 1, y sub 2. Verify by direct substitution. Explanation: important short answer question: derive the formulas for u1 prime of x and u2 prime of x in the general case. Start with the assumed particular solution y sub p equals u1 y1 plus u2 y2. Y prime equals u1 prime y1 plus u1 y1 prime plus u2 prime y2 plus u2 y2 prime. Y double prime equals u1 double prime y1 plus 2 u1 prime y1 prime plus u1 y1 double prime plus u2 double prime y2 plus 2 u2 prime y2 prime plus u2 y2 double prime. To keep the equations manageable, we impose the auxiliary condition. u1 prime y1 plus u2 prime y2 equals 0. With this condition, the terms containing u1 double prime and u2 double prime disappear from the expression for y double prime after substitution into the original ode, because they are multiplied by the zero sum u1 prime y1 plus u2 prime y2. The remaining terms lead to open parenthesis u1 prime y1 prime plus u2 prime y2 prime close parenthesis plus p of x times open parenthesis u1 prime y1 plus u2 prime y2 close parenthesis equals g of x. The second bracket is 0 by the auxiliary condition, leaving the simple linear system. u1 prime y1 prime plus u2 prime y2 prime equals g of x, and u1 prime y1 plus u2 prime y2 equals 0. Solve with Cramer's rule. The determinant of the coefficient matrix is exactly the Wronskian W equals y1 y2 prime minus y2 y1 prime. Hence, u1 prime equals the determinant of the matrix with first row 0 and y2, second row g of x and y2 prime, divided by w equals negative y2 g of x divided by w. u2 prime equals the determinant of the matrix with first row y1 and 0, second row y1 prime and g of x, divided by w equals y1 g of x divided by w. Thus the general variation of parameters formulas are u1 prime of x equals negative y2 of x times g of x divided by w of y1 comma y2 of x, and u2 prime of x equals y1 of x times g of x divided by w of y1 comma y2 of x. These expressions are the heart of the method and are what examiners expect you to write quickly in a short answer question.